Welcome back to the Explainer. Okay, let's dive into this. Last time, we painstakingly built out the practical equivalent circuit of a real-world transformer. Today, we're taking that complex model, stripping away all the friction, and calculating the real-world performance metrics that actually matter. We're talking voltage regulation and efficiency. So, no preamble today. Let's just get right to the math.
Now, if you recall from part 1, we had that somewhat messy T-equivalent circuit. Primary components over here, secondary components over there, and an excitation branch just sitting right in the middle. It was highly accurate, sure, but incredibly tedious to solve. Well, the promise for today is that we are going to collapse that entire practical equivalent circuit into a single, highly solvable loop. One circuit, one side.
So how do we actually get everything onto one side? We refer the secondary impedance back to the primary. And to do that, we multiply by the turns ratio squared. That's exactly what this formula is showing us. R2 prime equals A squared times R2, where A is our turns ratio. And you do the exact same thing for the secondary reactance. X2 prime equals A squared times X2. By scaling the secondary values like this, we're essentially sliding them right across the ideal transformer boundary. And the best part, in the process, we can peel off that parallel magnetizing branch separately because honestly, it draws so little current compared to the load that it barely affects our loaded performance.
Now, what's really interesting about this slide is how beautifully simple everything becomes once we do that math. The entire practical circuit just collapses into a single series impedance. We lump the primary resistance and the referred secondary resistance into one equivalent resistance, or REQ, do the exact same thing for the reactance to get XEQ, and that's it. You just have this one equivalent series block feeding your load with the excitation branch neatly tucked away at the input. This right here is the simplified equivalent circuit we'll use to calculate our two big real-world metrics.
Section 1. Voltage regulation. Understanding voltage sag.
Okay, our first major application of this newly simplified circuit is calculating how much the voltage sags. Because a real transformer has internal series impedances, that REQ and XEQ we literally just found, the output voltage is actually going to vary with the load, even if your input voltage is perfectly constant. We measure this effect using what's called voltage regulation. By definition, voltage regulation is the no-load voltage minus the full load voltage divided by the full load voltage, all multiplied by 100 to give you a percentage. In plain English, it tells you exactly how much the output voltage sags when you go from drawing zero current to drawing maximum rated current.
Now, for a totally ideal transformer, your voltage regulation would be exactly 0%. Zero internal impedance means zero voltage drop, no matter how much load you connect. But in reality, regulation is always greater than zero. That sag is driven directly by that equivalent impedance we calculated. And this is exactly why utility companies completely obsess over transformer impedance ratings. A lower equivalent impedance means tighter, much better voltage regulation, which keeps the lights in your house at a consistent brightness, whether it's 3 in the morning or the absolute peak of evening demand.
Section 2. Efficiency. Power lost as heat.
Let's shift gears slightly and talk about efficiency, which really comes down to power lost as heat. Efficiency conceptually is straightforward. It's output power divided by input power. But we can expand that input power denominator, because input power is really just your output power plus all your internal losses. So efficiency equals output power divided by the sum of output power, core losses, and copper losses, times 100. And the transformer equivalent circuits we use make these calculations incredibly easy, because we've already accounted for exactly where these losses happen using our resistors.
So, the crucial point here is understanding the stark difference between these two types of losses. Core losses, which are the hysteresis and eddy currents happening in the steel core, are constant. They happen the second you energize the transformer, even if it's completely unloaded and just sitting idle. Copper losses, on the other hand, are highly variable. They happen in the winding resistance, and they grow with the square of the load current. And this brings up a really fascinating engineering dilemma. Let's do a quick check to challenge your intuition. Imagine a standard distribution transformer sitting out on a neighborhood utility pole. It sits lightly loaded for the vast majority of the day. So, should you specify a design that is perfectly optimized for full load efficiency? Take a second and really think about that.
The answer is a resounding no. Here's the twist. Peak efficiency in a transformer actually does not occur at full load. Maximum efficiency hits at the exact mathematical point where your variable copper losses equal your constant core losses. For instance, if you have a unit with 1 kilowatt of core loss and 4 kilowatts of copper loss at full load, its efficiency curve actually peaks right around half load, not full load. Since a distribution transformer spends most of its life lightly loaded where those constant core losses really dominate, utilities deliberately specify low core loss designs for exactly this reason, even if it costs a bit more copper up front. The golden rule? You always design for the actual load profile.
Section 3. The per-unit system, a vital tool. Okay, before we wrap up the math entirely, we need to introduce a vital macro-level engineering tool. As we saw earlier, solving circuits with multiple transformers can be incredibly tedious because you're constantly referring voltages across different levels. The per-unit system totally eliminates this headache by measuring electrical quantities as decimal fractions of a base level. To find your per-unit impedance, you just divide your actual impedance in ohms by a base impedance. And you get that base impedance simply by taking the nameplate voltage squared and dividing it by the rated apparent power, or the S value in VA.
And this brilliantly illustrates why power engineers absolutely rely on the per-unit system. It completely strips away the physical size of the transformer from your math. Power transformer impedances typically fall into a very narrow range of 4 to 8% in the per-unit system. This is a total game changer because it allows you to directly compare a 500 kVA distribution unit to a massive 50 MVA substation unit on the exact same scale and use both directly in fault current calculations without ever doing those tedious voltage level conversions back and forth.
Section 4. The physical reality. Surviving the elements.
Well, we've covered a ton of ground today. You came into this knowing how a transformer is built, and you're leaving knowing how to model it as REQ and XEQ and calculate both its voltage regulation and its efficiency at any given load point. But theories and math eventually have to survive out in the physical world. Just look at a standard distribution transformer. You've got the solid exterior tank, heavy corrugated bushings up top to isolate the high voltage lines, the winding core submerged inside, and the thick steel shell enclosing the whole shebang. All that pristine math we just learned, the equivalent resistance, the carefully balanced core and copper losses, has to operate reliably inside the sealed tank, subjected to lightning strikes, blazing sun, and freezing rain.
Which leaves us with a pretty provocative question. How does this raw physical hardware actually protect the delicate equivalent circuit we just mathematically modeled from those harsh elements? Well, that is exactly where we are heading next. We've had enough circuit theory for now. In our next explainer, part 2.3, we are going inside the tank. We'll explore the component engineering, the actual protective hardware, like the bushings, the relays, and the tap changers that monitor this circuit and make these machines truly survivable in the field. You definitely won't want to miss it. Thanks for joining me on this explainer, and I'll catch you next time.